Here's a Bayes' theorem example with medical testing. And typically, what happens with medical tests is you have a couple different events that you care about. You have, say, A is the event that the test is positive, and then a complement, of course, test negative. And then you also have the event that you are positive. You actually have whatever you're being tested for. And then complement, event, event, you are negative. Okay, so we have those two things, and typically, what happens is you go in for a test and say it's positive. You want to know this probability. What's the probability of you are positive given the test is positive, right? So that's what you want to know. And typically, we don't exactly have that information available to us, but we can look up things, and so somebody who's done this already with all the numbers knows, but you and I who just go in for the test, we don't tend to know. And so typically we're given things though like, well, the probability of B that you might have this in the general population. You might, we might know what that is, and maybe it's 10% of the population, which actually for many things that we test for, that's pretty high, but we'll go with 10% on this first one. And so then the probability B complement is just 1 minus that 0.1 or 0.9. And then similarly, we do know things from our testing procedures and so forth that, from getting tests approved and that kind of thing, we would know something like P of A given B. Okay, what's the probability of testing positive if you are positive? And, who knows? Let's say it's 85%. We're just picking some numbers here. And then similarly, we might know, what's the probability of testing negative given you are negative, and, maybe that in this case is even higher, maybe 0.95. So those are the numbers we know. So you see, in order to get at P of B given A, it's actually, we'll want to use this probability of A given B, because that we have right there, times the probability of B over the probability of A. Okay, now, but the problem is I don't have the probability of A typically, and so this is, what was the, it's interesting with COVID, we are hearing that sort of number, but it's, what the heck do we call that? Positivity rate or something like that. But typically, yeah, we don't know the positivity rate. And so what we would do is, as in the previous video, we would use B and B complement as our disjoint sets to come up with A, and we would have our P of A given B times P of B, and then plus P of A given B complement times probability of B complement. So there's our, we just have two disjoint sets, but there we have them. And so now I can evaluate all those things. So this is equal to, I'll put it down here. So this was the 0.85 times the probability of B, which was 0.1. And then over 0.85 times 0.1 plus 0. We have to look that up because we're given A complement given B, but not A, or sorry, we're given A complement given B complement, but not A given B complement. But that's just the probability of A given B complement is 1 minus 0.95 or 0.05. And so I have 0.05 times 0.9. And so I do that calculation. Now I've done that calculation, and it turns out this simplifies to 17 over 26. Now that's almost like 18 over 27, which would be 2/3. So, you know, I said that's about 2/3. Okay, so now all of a sudden, notice that this says if I go in for a test and it's positive, there's actually only a 2/3 chance that I have the thing that we're looking for. And that sounds kind of bad. And actually, I'm going to pursue this a little further. We'll see it would be really bad if the population of those who have it generally was much smaller than 10%. And that's why these tend to be kind of bad. And that's no matter how good these other things are, the 0.85 and the 0.95. And so often textbooks make that out to be a big deal, you know, as a bad thing. But, however, if you instead were to do the same calculation for the probability of B hat or B bar complement given A, and you know, doing P of A complement given B complement times probability of B complement, and then divided by the probability of A complement given B complement, probability of B complement, plus the probability of A complement B times the probability of B. So if we did that, this turns out to be, I don't have it reduced, but I've got 855 over 870 for something I calculated. But that turns out to be about 0.98. So, you know, this one is 0.65 actually, not quite 0.667. But see, this is 0.98. So it says if my test is negative, then I am 98% certain that I am negative. That sounds pretty good. And for most things, that's a big deal. You don't want to test to say, oh, you don't have cancer when you really do. And so these tests, it's a much bigger deal to have this number, the probability of B complement given A complement, or the probability of not having whatever you're testing for given you tested negative, that you want to be a very high number, and it tends to be. So here we're up at 98%, and so that's a good thing. Now, to look at this a little further, you can actually do all this if you had real live data instead of just these probabilities that we're given. But if we were given real live data, so, here's actual, and here's the test, so this is A, this is B, and so here's our positive, and here's our negative. Okay, so, and say you actually had it or didn't have it. And so let's go with, we have 100 people who actually have it, 900 people who don't. So this is just, you went out and checked the population. This was actually the case, and so that's 1,000 people total. And so according to our initial numbers, of those who have it, 85 of the 100 should test positive, and 15 will test negative. And similarly, if we look at our 85% or 95% of 900, that's 855. So 855 people who are negative should test negative, and another 45 should give us a false positive. So adding these, I get 130 and 870. Now, so if I want the probability of actually having it given a test positive, that's okay. I actually have it 85, but the test was positive. I have to look at this row, and so I'm looking at 85 over 130. Okay, I can just give that number, and there it is. And that is the numbers I got back here, the 17 over 26. Okay, if you reduce that, so that's 0.65. Now, similarly, suppose the test were negative, and I want to know, was I negative? I want to look at those two numbers. So the test is negative. I'm looking in here, and I look at, well, how many were negative, actually negative, over how many were given. And so the probability of B bar given A bar is equal to 855 over 870. So that was the 0.98. Now, to switch this up a little bit, let's say instead of 10%, it was just 1%. And so now I'm going to make this same thing. Okay, there are my 3x3. So here's actual, positive, negative. Here's the test, positive, negative. But now I'm just going to have 10 out of that 1,000. Now, so I'm going to have to go to fractions here just because I wanted to keep it as 1,000. So 85%, that would be 8.5 of them, which leaves 1.5. And similarly here, if I take my 95% of 990, that's 940.5. and 49.5. So if I were to actually do this with 1,000 people, this is kind of what I would expect to see. And this would be 58 and 942. And so, though, once again, if I look at my P of B given A, now if I test positive, how likely am I positive? Well, that's the 8.5 over 58 because I did test positive. So that's 8.5 over 58. Or now I'm down to 0.147, or just about 15% likely that if I tested positive, I actually am positive. So all of a sudden, that looks like these tests are terrible. But if I test negative, that's the probability of B hat given A hat. That's 1.5 over 942, which is 0.998. And so that says, hey, if I test negative, I am 99.8% sure that I do not have it. That's a win right there. And so, these things are a bit counterintuitive is what this is showing, is that even though my test, 85% of the time, if you have it, 85% of the time, the test shows you have it. That sounds great. But it turns out if what you're testing for is somewhat rare in the population, that positive test isn't really going to tell you that much. But on the other hand, a negative test, that will tell you a ton. Okay, so there's an example with Bayes' theorem and taking it through some different possibilities. So the book tends to just give you this information right there and then ask you to calculate something. But, what are we calculating? What's going on and how might some things be counterintuitive? And it turns out that if these probabilities are very, very different from each other, and that would include the sum, a collection of more than just two, a B and a B complement if you had a B1, B2, B3, and so forth. If they are vastly different from each other, the collection. So if the one you're looking for, the one I'm looking for, is vastly different from everything else, it turns out that the conditional probability here is going to be very, very different. The reverse conditional probability, that one, is going to be very, very different from this one. So, but on the other hand, these may not be that dissimilar, opposites there. But so it's just interesting with the Bayes' theorem, but it does have a lot of nice applications and actually for things like machine learning and that kind of thing, it has a lot of great applications to gather. So basically to learn by doing what they call Bayesian updates, which has to do with Bayes' theorem here. Okay, so we'll call that example done.